Okay, so from today, we will gonna learn about how we can use the PyTorch to implement the deep learning algorithm. So this is something we learned from by previous lecture. So inside the deep learning architecture, we can stack multiple differentiable layers. Okay, and those differentiable layers have to have two types of gradient, okay, which is the differentiation of output respect to the input and also respect to the parameters, okay. And this is the gradient descent algorithm that can update iteratively our parameters, okay. So our ultimate goal is to minimize the loss, and that is actually these gradients having the direction where reducing the loss L. Okay, so in that direction, we are updating our parameter sector. Okay, but important thing we have to remember is implementing this gradient descent and calculating this gradient by ourselves takes many effort. Okay, so when implementing those formula inside the Python, maybe forward rule is simple. Okay, so we can just use some operators that can connect x and parameter sector to output y. But to implement this dy dx and dy d sector, we have to first calculate closed form solution for this gradient. Okay, dy dx and dy d sector. Okay, and important thing is the difficult thing is this dy dx and dy d sector always changes whenever the forward function, the f, changes. Okay, so for example, when f is just like this, which is the simplest form, okay, then if you want to differentiate, maybe this is y, okay, sorry. Y is equal to fx, and that function is this. If we want to differentiate this respect to x, then it would be simply this, okay? But anyways, we have to calculate this kind of closed form solution for this differentiation, right? And have to implement this in the code level, okay? And also we have to calculate that dy dissector is, for example, this, and have to implement this in the Python, maybe, to implement this layer by ourselves, okay? But good thing when we use this PyTorch library is we don't have to care about this backward path, okay? Because the PyTorch can calculate all of the gradient in the numerical way. Okay? So without calculating this type of closed form formula for each gradient, the PyTorch can calculate the gradient value for each, for any forward functions. Okay, so you may learn about some numerical calculation method for gradient. Okay, in calculus course maybe. For example, the Newton's method maybe. So it iteratively approximates the gradient for certain point. Okay, are you guys understanding that? Or already know about that, right? So anyways, in the computer, we can approximate the gradient value without calculating this type of closed form formula for the gradient. Okay? We humans have to calculate this, okay? But the PC, the computer, do not have to do that. Okay, they can iteratively approximate the gradient value, and PyTorch in already embedding those gradient calculation modules. Okay, so if we do this track, if we don't have such automatic gradient calculation module inside the function, then we always have to calculate write down this type of closed form formula for the gradient and type it hard coded in the Python language. Okay, but thanks to this PyTorch library, we don't have to do that. Okay, instead, what we have to do is just calling these two lines of code to automatically calculate the gradient values for all the node inside the deep architecture, and also to calculate using that gradient. Especially, I will explain that further in the later slide. But when you call this load stop backward, all the nodes gradient is automatically calculated. Okay, and then if you call this second function, optimizer.step, then using that gradient, we calculate DL dissector eventually, and also you can update the new parameter sector using this gradient. Okay, that is happening when you call this optimizer.step. Okay, are you guys following that? Okay, so if you already I'm assuming that you are already seeing some of the PyTorch code. There's always, in the training code, there's always these two lines of code in the PyTorch, okay? But the first one that is automatically calculating the variable. And second, you can update them using those, the gradient, okay? You have to remember that. I will show you the simplest form of the machine learning algorithm, which is the linear regression algorithm using the PyTorch now. Okay, I will start from that, and eventually we will implement the CNN architecture using the PyTorch. Okay. Linear regression is the simplest form of the machine learning algorithm, and which uses just the linear mapping, linear equation between to map the input x towards the output y. Okay, so this is the input x space, and this is the output y space. Okay, and we are given 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data. Okay, during the training stage, we are given 10 number of maybe n is equal to 1, 2, n is equal to 10. Okay, 10 number of data pairs, the x and y pairs. Okay, and wanting to learn w and b. Okay, are you guys following this? Okay. This W and B is the parameter sector we are wanting to learn. Okay. And after learning this W and B in this linear equation, we can input new X value to this function and and we can get the corresponding Y predictions. Okay. So, and we are wanting this Y prediction is plausible. Okay. That's what we are wanting to achieve in the when using the machine learning algorithm. Okay, and this Wx plus b is modeling the linear, the linear line, the straight line like this. Okay, and given this 10 number of data, we have to somehow get this W and B, which best explains this 10 data point. Okay, are you guys understanding that? Okay, and there could be a lot of possible straight line in this 2D space, but the one is selected which can minimize the somehow the loss between. The loss L is defined by the distance between Maybe you already know about this. So this is the predicted value, and this is the ground truth value for that data point. Okay. So our purpose is wanting to make the prediction Wx plus B close to their corresponding ground truth. Okay. And this is how the loss L is defined. Okay. For 10 data samples, we want to minimize their distance between ground truth and their prediction. Okay. Are you guys understanding this? Okay. And this is the loss L. And I mean, we are selecting the straight line that is minimizing this loss L. Okay. And we can solve this. There could be several solutions, several methods that can optimize this loss L. Okay, we can select W and B. There are several methods for selecting W and B by minimizing this loss L. But the gradient descent algorithm could be also used to minimize loss L when selecting W and B. Okay, so the next slide is showing that code. Okay. So this part is for generating some data. Okay, so but this time the W is not a scalar value, but we are assuming that 3 by 1 vector. Okay, so we are assuming the X could be some vector here, and B is some scalar value. Okay. And this is some true W and B. We are wanting to find this W true and B true via this optimization step. Okay, but the W and B that we will optimize is randomly initialized. Okay, that is actually randomly initialized with the same dimension to the W true and B true, but having some random value at the initial status. And we are wanting to make some X and Y pairs by using the W true and B true. So X is randomly sampled for 100 samples. We randomly sample X for 100 times. And then we multiply W true and add B true to that randomly sampled 100 samples. Then this Y becomes ground truth value. Okay. These X and Y pairs, we can think this X and Y 100 samples as the training data to fit this W and B. Okay. And gamma is some scalar value. And this is actually the the value which will be used here. Okay. So in the gradient descent value, we need some scalar value, which is a small scale. So this gamma, you can think this as the gamma. Okay. And X, the sector now is the W and B, and we are actually randomly initializing them. And the remaining thing is we will calculate the loss and calculate the gradient of loss respect to their parameters. And then we will add them to the initial parameters iteratively, okay, by seeing the training samples, and will continuously update the parameters. Okay, are you guys following that? Okay. And this is actually the loop for that. So we will loop through the 100 iteration. Okay. But this is the PyTorch style code. Okay. So I will explain that later. Okay. Anyways, what they do is they first how to say, apply those X samples with the forward function first, and this is the predicted Y. So from the X, we multiply the initial W and add B to predict something and calculate their loss. Okay, this is the loss. And by calling the loss step backward, they calculate this DL dissector. and then add it like this. Okay, this is the gradient descent formula. And they do this 100 times by, to iteratively update the parameter, their W and B. Okay, so by doing that 100 times, we are assuming that the W and B are gradually updated, okay, in the direction to minimize the loss L. Okay, are you guys following that? Okay. But here, there's no explicit formula. There's no explicit code for calculating this DL dissector. Because we are using the PyTorch, okay? Because we are using the PyTorch. So this is some, this is the iteration number. And this is the loss L, okay? So you can see when iteration goes, because the W and B are gradually learned, so their loss functions are gradually reduced. Okay, so that coincides with our objective that minimizes the loss L, which is the distance between ground truth and our prediction. And you can see the obtained W is 1 to 3, and the obtained B is 5. And the true W and true B, you can see they are identical to the predicted obtained W and B. Okay, so via this gradient descent algorithm, you can now confirm that we can find the true W and true B from the random W and random B values. Okay. This is the PyTorch code, but let's assume that if you implement this type of things using the NumPy library. So, without using PyTorch, the NumPy is the library in Python which can implement the array, which can easily deal with the arrays. Okay, so if you use only the NumPy, okay, then you also have to make some W true, B true, and WB, randomly initialize WB, and also have to generate some X and Y pairs, 100 pairs, okay? And set this gamma and loss function. And inside this loop, you have to implement the part we learned, okay, using the PyTorch. Okay, so here we have to explicitly calculate the loss function. Okay, and also you can see this type of gradient. Okay, DEDW, because we define the loss here as the error, so we denote it as E. Okay, anyways, we have to define calculate these two types of gradient, okay, by ourselves, and then implement that in the code level. Okay, are you guys following that? Okay. So, because somehow this is the loss function, okay, and but normally we use multiply some 1/2 to this loss, okay? And if you want to, maybe E, we can denote it as E, okay? Maybe you have to calculate it by yourself like this. So maybe first you have to multiply this and also multiply some term that also differentiate this again here, right? And also DEDB, you also have to do similar things, okay? B, and there will be 1 multiplied. So this is the hand calculation, and you can see this term is same as this. So because we define errors as this term, okay? So DDB is same as this term, and also DDW multiply this x. This is anyways calculating this type of gradient formula by ourselves and implement that in the code level. Okay, are you guys understanding this? Okay. And also you have to calculate loss and then implement this gradient descent again. Okay. That is the way of implementing this linear regression without using PyTorch in Python. I mean, even in the simplest case, it is a little bit, how to say, not very trivial to calculate this kind of gradient formula by yourself and implementing that in the code level. Okay, so if you are not given this code, it might be, could have involved some mistakes. Okay, so it is not that simple to implement, but even deep learning architecture having more than one layers, the situation is becoming worse. Okay, so calculating all the gradient by yourself and implementing that in the code level is becoming the tedious job. So the PyTorch is helping you, okay, to avoid those kind of boring tasks. Okay. Uh, by replacing this gradient descent calculating this type of closed form formula by yourself, they are implementing some numerical modules to calculate the differentiation of last node, which is the loss, respect to those node automatically, okay, by using the numerical approximation, okay. And if you call this load step backward, that modules are actually automatically called. Okay. And also these the later terms are also becoming could be become more simpler. So I will show you how we can make them more simpler. Okay. But before that, I have to explain this. So uh, so when how I mean uh, sometimes you may think that this one line of code is too simple, right? And maybe curious how they know which type of nodes are connected. So uh, I will this slide is some of the providing some of the explanation for that. So this could you can regard this as the last node, which is the loss. Okay. And inside the PyTorch, somehow there are intermediate torch variables. So always when using the PyTorch library, you have to make those variables as the PyTorch variable. So in the NumPy, you have to make them as the NumPy array. But in the PyTorch, to make them in the usable in the PyTorch, you have to make them as the PyTorch arrays, okay? And BXW, those PyTorch arrays are always having these two types of instance variable. So the first one is the data, and that is holding the values, okay, their values. So B, for example, is having some randomly initialized bias value. Okay, X is the X data values they are what they are holding. Okay, W is also parameter value they are holding. Okay, and B dot grad, and again, if you access their data instance variable, this variable is holding the gradient value. Okay, so gradient means the differentiation of the last node, the loss L, respect to this node B. Okay, they are holding this gradient DLDB, the differentiation of last node respect to that. I mean, respect to this node that is holded in this b dot grad instance variable. And for example, here in this x dot grad, they are holding this type of gradient value. Okay, but at initial status, they are having some random value, okay? At the initial status, they are having some random value. But because of that, you have to assign known variable, known to those W and B, which is the parameter sector, okay? Uh, I will explain that again, maybe. If you do not do this, uh, because the W grad and B grad, they are having some initial random values. So the learned gradients are added to them. So eventually they will have some wrong gradient value. Okay? So it's similar to what you do in the C programming language. You do this type of initialization because the A variable is having some garbage value at the initial status, right? So to use that properly, you have to initialize A to have 0, maybe, okay? So this is similar to that, okay? So for the parameters to learn, you have to initialize them. And also, these intermediate PyTorch variables are connected together via this type of operators, okay? So, I mean, you define this type of forward rule to calculate the final node loss L from the intermediate node. You already specify them in the PyTorch code, right? We always have to specify how to feed forward, which means how to get the final node L from the intermediate variables. You have to specify that, okay? And inside the PyTorch is building this type of structures that can connect intermediate variables, PyTorch variables defined using the operators, okay? So they are building this type of graph to, estimate the final loss L, okay? So thanks to this structural, graph, the PyTorch already knows which nodes are connected from this final node L, okay? So, using that and using the backpropagation algorithm that we learned last time, here no. So previous time I show you how the computers are calculating the differentiation for the deep layers, deep stacked layers, step by step from the last node to the initial node, right? You already learned about that last time, okay? So using this as the structure, from the final node L, they are step by step approximate each layer's gradient and multiply them via chain rule to calculate DLDB, DLDX. Anyways, the differentiation of last node L respect to all the intermediate variables, okay? When calling this simple line of code, okay? Are you guys following that? Okay, so when the PyTorch, by calling just loss dot backward, because you already defined how your final node L is defined from the intermediate PyTorch variable, they already defined this type of graphs, and they already know which nodes are connected in which way from the loss L. So by calling this loss dot backward, you can calculate the differentiation of loss L respect to all the nodes in the middle, right? And then if you calculate those gradient, then the remaining thing is just adding them to the initial parameters by multiplying some gamma value, which is the small scalar value, and and you will add them to the parameter, original parameters. Okay.
Is gamma here like a learning rate?
Learning rate, yeah, it's learning rate. So yeah. Some scalar value, okay, and you have to heuristically adjust that to make the learning goals, okay. Okay, so this is somehow easy, but not to miss. We don't have to miss that when learning this PyTorch part, okay. And also, this code is already trivial to use. but the PyTorch is providing more abstractions. Okay, so for example, here we are explicitly implementing the linear regression formula like this. Okay, but in the PyTorch, they are wanting to make it more abstract. So they are wanting to make some net variable instead of using just W and B. Instead of directly accessing the W and B, they are wanting to access some net variable, which pointing the network itself. Okay, not pointing the how to say the parameters themselves. Okay, it is more easy to implement big architectures. So when you let's assume that you are implementing some big network having many parameters, then they are having maybe 100 lines of parameters. Okay, so now we are implementing this simple linear regression having just W and B, but if we implement big architecture having 100 parameters, then we need 100 lines of code for this. Okay, to avoid that, the PyTorch is wanting to implement the code in this way, not pointing the parameters themselves. They are wanting to make some net variable for the network itself. Okay. And in the PyTorch, the frequently used layers are already defined. Okay? Frequently used and also differentiable layers are already implemented in the PyTorch. And also, if there's no such layers implemented in the PyTorch library, then you can also implement by yourself. Okay? You can add them. Okay. Anyways, this is the torch.nn linear layer, which is defining this type of linear layer. Okay, you can just specify their input dimension and output dimension and whether to use the bias or not. Okay, so bias means this B term. So we are using that normally. So true, and our output is 1 dimension and input is 3 dimensions. So we can initialize the network that we are using like this, okay? And instead of writing down these formula themselves, you can just call this net network and input inputting the input X, okay? So you can implement the same thing in this way, okay? And also the gradient descent form is also sometimes heavy to implement by yourself. Similarly, if you have 100 parameters when implementing the big architecture, then you need 100 lines of code for implementing just same same thing, because there are 100 parameters, you have to implement the same line of code 100 times, okay? To avoid that, the PyTorch is providing this type of optimizer modules, okay? So which is implementing the torch.optim dot. Inside these packages, there are several optimizers already defined. So because we will use the simplest form of optimizer, which is the gradient descent algorithm, we can just call this SGD, okay? And also there are 2 arguments for this optimizer, okay? One is net.parameters. This is meaning net is the network we are using, right? And if you access this dot parameter instance variable that returns the parameter sector, they will run. Okay. And also this gamma is the value we define here, which is the small scala value. And that is actually the epsilon value in the gradient descent form. Okay. So I will rewrite the gradient descent formula here. Okay. Then here, when defining the optimizer, we already provide some parameter list, okay, and also the epsilon, okay, when initializing this optimizer, okay. And the remaining thing is to calculate this DLD sector, which is the gradient, where to update the parameters. We will calculate that automatically by calling this loss dot backward, okay. And then the remaining thing is when after calculating this gradient, or everything we know for in this formula. So after calculating this gradient, we call this optimizer dot step instance method to calculate ones for this formula. Okay, are you guys following that? Okay. So and also here, one more thing they are providing for implementation simplicity. So here you can see optimizer dot zero grad. So previously it was like this. So we by one for parameters, you have to type, you have to assign known value variable for known value for that each parameters, right? But now optimizer already have the parameter list to learn. So if you call this simple one line of code, then the optimizer, they assign known value to those variables, okay? So here, everything is becoming more simpler now. So previously, you have to access each individual variables by yourself and assign known variable and calculate the gradient descent by yourself. But here, by defining this optimizer that is already having some parameter list and the running rate, you can call just one line of code to initialize all the parameters to learn. And then also by calling this loss dot backward, you can calculate the DLD sector. And by calling this one line of code to calculate, to update ones for the parameters, okay? Are you guys understanding that? Okay. So now the training code is becoming very simple. So you will loop through this code for any types of network, okay? This simple line of code is reusable for any types of actually code. But before that, one more thing have to be become simpler. I will show that. The other thing have to change is previously we are using the Euclidean distance as the loss term, okay, to close the predicted value to the ground truth y, okay. But there could be another loss functions as well, right? So for that kind of encapsulation, actually we define also some modules for the loss functions as well. So when calling this type of Euclidean distance between ground truth and predicted value, you can just call this MSE loss. MSE loss means mean square error loss, okay, which is same as the Euclidean distance, okay. And the thing you have to do is instead of typing this type of Euclidean distance by yourself, you can just call this loss function. And as the argument, you can input the y predicted value and their ground truth. Okay. So, and then now this code could be usable for any loss function, any network architecture, and any optimizers. Okay. And also their code, their result is same across this type of code and previous code and NumPy code and so on. Okay, so this is again the PyTorch style, the training code. Okay, you will always see these lines of code when implementing the training using the PyTorch. Okay. Okay, I will indeed show you for any architectures you can use this type of same code. Okay, I will show you. Okay. till now, we learn about the simplest form of the machine learning algorithm, which is the linear regression, but we will see more complex version of the machine learning algorithm, which is called as multi-layer perceptron, and we normally call as the MLPs. Okay. So I mean, so perceptron is the some modules in the brain, and when these deep architectures are quite having quite long history. So, but I mean, they are inspired from the human brains having some very naive, simple modules, and by stacking them multiple times, the brains are becoming very complex. So, inspired from that, the MLPs are coming. Okay, so they are stacking very simple linear operation multiple times and wanting to achieve some, how to say, the complex tasks. Okay. So this is actually the form of the MLP. So they are first having the linear equation and having some nonlinear layer, and also having another linear layer and having nonlinear layer again, and stacking another linear layer and having another nonlinear layer. Okay. Are you guys understanding this figure and this formula, right? So they are stacking multiple nonlinear linear layers sequentially. And also, I will show you, in previous lecture, I mentioned that I will explain why this type of activation layers are required in the deep learning architecture. Okay. So this sigma is actually denoting the nonlinear functions that we learned last time, like the sigmoid, tangent, hyperbolic, and ReLU functions. Okay. These functions are differentiable. ReLU is sometimes not differentiable, but that's enough for the deep learning. Okay. Without these sigma functions, uh, if you rewrite the overall function, their variables without this sigma function here, then you can see the huge, I mean, their, how to say, variables are simplified to be another huge linear equation. Okay. Are you guys understanding that? Okay. So if you simplify the right side term, then that is simplified by these two terms, which is multiplied by x, and another terms are having some constant. Okay, this is another form of simple linear equation. It's not representing any nonlinear functions. Okay, so without involving this nonlinear deep learning architecture, even though they are complex, having many operations, having big architectures, they are becoming simple linear equations. Okay, so that's why we are involving this sigma to avoid them becoming the huge simple functions. Okay, and when implementing these MLPs in the PyTorch library, the thing you have to do is just changing the network definitions. Okay, so you will see the later part will be saved to the those of linear regression code. Okay, the training code, definition of the loss and optimizer, and the for loop, they are same as the one we implemented for the linear regression, but the thing changed mainly is the network architecture and the data generation part. Okay, so here the sequential means stacking multiple layers sequentially. Okay, so we are stacking linear layer, ReLU layer, linear layer, ReLU layer multiple times. Okay, so that is actually representing this type of formula. Okay, so this is actually the MLP implementation, and the data for the data we will generate 1,000 data pairs. Okay, and this is the epoch, which is the iteration number for the training. And this is the data generation part. For the X, we will generate 1,000 random variable. And for the Y, for the Y, we will generate this type of we will generate the output ground truth by using this formula, okay? And somehow, when by using this training code, we are using MLPs, okay? So we are wanting to make this MLP, which is having 3 layers of the linear layer, mimic this, quadratic function, okay? And if you run this code, maybe in the Google Colab, they will run in few seconds, and you can see this type of graph again. So this is the iteration, and this is the loss L. And from the early epochs, you can see the losses will be reduced gradually. And also, this is showing the result. So this is the X for generating some random 5 testing samples. Okay, and this is the Y generated by this true quadratic function. And this is Y predict that is generated by the trained network that mimics these quadratic functions. Okay, and you can, if you print out these 2 variables, then you can see their values themselves could be not same, but their tendency are becoming similar. Okay, so indeed the net here is trained to mimic the quadratic functions. Okay, are you guys understanding that? Okay. And now we will learn about how to implement the CNNs now. Okay. So yeah, this is the CNN architecture we have learned. Okay. They are composed of 2 parts, the convolutional layers part and fully connected layers part. And fully connected layers part that these things are processing the 1D signals, and that is actually same as MLP. Okay, so those are actually same as the one that we learned now, okay, just before. Okay, this type of layers are used for the later part of the CNNs to further processing the one-dimensional signals. Okay, and when implementing these CNNs, more advanced architecture, the implementation techniques are required because CNN is a little bit large in scale. Okay, so we involve the class, class grammar in Python. Okay, so wanting to define some class, okay, for some CNN architectures. Okay, and we actually have 2 methods for that. The first is the init method, which is the constructor of the class. And the second is the forward method. Okay. Maybe you already familiar with the OOP, right? When implementing OOP, this constructor is once executed when initialized. Okay. So this initializer is samely operating in because that's class grammar in Python. They are operating samely as before. They are once executed when this network is initialized. And forward method, they are called what that we want to do forwarding, feed forwarding. When calculating the output value from the input, okay, that's forwarding. So these forward functions are called when we want to do that, okay? And because this part is called when network is first initialized, so we normally implement the network structures here, okay? So we normally implement the network structures here because those parts are, once executed when initializing the instance of this class, okay? So this is implementing the convolutional layers, Okay, by sequentially they stack convolutions, ReLU convolutions, backspling convolutions, ReLU, maxspling, and this is the convolutional layers. And the later part, that is MLPs. Okay, they sequentially stack the linear layer, nonlinear layer, and linear layer. Okay, so here they implement the network structure, and their parameter sector is randomly initialized. Okay? And this is defining forward function. They are defining the how to feed forward from the input to calculate the final output. Okay, so this is the image X, and you first input it to self dot layer you define here, and here this is the and there's no star here, sorry. So anyways, this is implementing the flattening operation. So after convolutional layers, the outputs are still in 2D space, but you have to flatten them into the 1D, okay? That is implementing that. And then after doing that, you will feed forward that to the fully connected layers, and that becomes the final output, okay? So the CNN, when implementing CNNs, you always have this type of grammar, okay? And there should be a backward function here as well. If you do not use PyTorch library, okay? If you use only the NumPy library, for example, to implement this type of deep architecture, then there should be another method that specifies backward, okay? You have to calculate their closed form formula by yourself and have to implement that in the method. Okay, in the code level, you have to implement that. But these parts are already implemented in the PyTorch using some automatic the numerical calculations in the upper classes. Okay, so you will just inherit that for your individual individual network. So you don't have to implement now for these backward functions. Okay, are you guys understanding this? Okay. So the thing you have to now consider when implementing the CNN architectures is their structures and their feed forwarding method. Okay, you don't have to care about their backward calculations. Okay, but you have to carefully design their this type of hyperparameters and parameters. So this is you have to check it for PyTorch website, and this is the input channel number, output channel number. For example, this is the filter kernel size, and also you have to properly design the zero padding number and also the stride. Okay, and this always calculate. You have to calculate those intermediate output, and I mean, if your flattened variable is not fit to the input to this, how to say, input dimension of the subsequent layer, the PyTorch will output the semantic error. Okay, in the runtime, if their dimensions are not same, then it will provide you some error message. You have to carefully design their dimensions. That is the only thing you have to care about when implementing this type of SIGs. Okay. Okay, so now your network will be initialized via calling this my CNN class you implemented here. Okay, so you normally need to implement your CNN architecture and also using this training code, same lines of the training code, you can train your own CNN networks. Okay. So, I mean, I believe that any types of CNNs you can implement using this type of template. Okay. And now we will further learn about the image classification task, okay? Which types of loss functions could be used to implementing this image classification task. So, I mean, the Euclidean distance that we learned, we previously used. This is applicable when the y predicted values are having some meaning. Okay, when the task itself is the regression task, where the output value itself has some meaning, this type of Euclidean distances are used as the loss function. But in the classification task, okay, this type of loss functions cannot be used, okay, because in the classification task, the output, the CNN's output, this is the CNN, and if you input image, and output will be n-dimensional vector that is describing the probability for each classes, okay? So, I mean, you cannot simply use this Euclidean distance to this, okay? So we have to define another loss functions for this classification task. And also, okay. And also the last part, it also have to be probability, okay? In the regression task, for the linear regression, there could be any floating values, okay? But in the classification task, the final output have to be some probability vector, okay? So there's some constraint for the probability, so there's some have to be one, and their element have to be positive, okay? Non-negative. Their element have to be non-negative, okay? So the classification task, we need a few more layers that have to be fitted to this classification task. So we will further learn about that, okay? And image classification, as I mentioned previously, that is the task wanting to classify images according to the main object. Okay, so for example, these images are having airplane, airmobile. So we are classifying these images according to their main object. And also these images are having some digit. So we will classify these images according to their digit. Okay, that these images are containing. And for example, Caltech 101, that is also data set proposed by Caltech researchers and having 101 classes, okay? And ImageNet dataset, which is the largest scale ImageNet data, image classification dataset, having 1,000 classes, okay? Okay. And before learning about this classification task, okay, we have to learn about logistic regression task, which is actually perform the binary classification, even though their name is regression. And also, you don't have to be confused this to the linear regression. Their spell is quite similar, linear regression and logistic regression. What they do is quite different, okay? So don't be confused to that, okay? Linear regression is called as linear regression because they are having linear formula, okay? And wanting to achieve the regression task, okay? But logistic regression, they are having some of the nonlinear layer inside, but they are not having nonlinear functions. They are after that they are applying some sigmoid function. Okay, so here the nonlinear function is sigmoid. So this is the overall formula for this logistic regression, logistic regressor. Okay, and the thing they wanting to achieve is the binary classification. Okay? You will see now. The sigmoid function, this is the sigmoid function, and I already told you that they are defined from minus infinity. Their x variables are defined from minus infinity to infinity. but their y variables are bounded to 0 and 1. Okay, are you guys understanding that? So y variables are always bounded. Okay, we on purpose, this linear equation is not bounded. Okay, but we apply that to sigmoid function and wanting to bound these g values within 0 to 1. Okay, and the thing we want to further achieve is we somehow threshold their output z value. And if g value is larger than 0.5, for example, then we'll say that class is 1. And if g value is less than 0.5, we will call that sample as the 0 class. Though now they are having similar linear equations in the middle, but feed that to the sigmoid function and eventually get some value from 0 to 1 and threshold that. And if one sample's value is larger than some threshold, we will call that as one class, okay? And if the sample's value, output value is less than some threshold, then we will call that as another class, okay? So this is the classification, okay? Not the regression, okay? We will not use their low value that we can, of course, use these g values as somehow confidence values, but that is not our final output. But the thing we will use is the either 1 or 0, which is the class information. Okay. So logistic regression, they are having similar formulation somehow to the linear regression, but their philosophy is completely different from linear regression. Okay. They are wanting to achieve this binary classification. Okay. And I will start from implementing this logistic regression, which is the simplest form of classification task. Okay. And when training this logistic regression, we will not use MSE loss, which is the Euclidean distance. Instead, we will use binary cross entropy loss. Okay. And that is actually this. Okay. And you have to first understand these two types of formula is actually same thing. Okay. So here that is showing that if yn here is nth samples ground truth. Okay. Nth samples ground truth is 1. The loss value is this. Okay. And when nth samples ground truth is 0, we will define the loss function as this. Okay? So z here is same thing in this slide. Okay, but the output for nth samples. Okay, so we will apply minus log to nth samples output when their ground truth is 1. And we will apply this type of loss function when their ground truth is 0. Okay. And actually, that could be represented in this way. So when yn is equal to 1, this becomes 1, okay? And this becomes 0. So you can omit this term. And this simply goes to the same formula here, right? And for the samples whose yn is 0, this term completely goes to 0, but only this term goes to 1, and this term remains. So, you can see now, this is actually same formula as the below formula, okay? Are you guys understanding this? And now I will explain what types of things they are doing. So log. So this is the ln z function maybe. This is ln z, this is z, okay? And their log functions always looks like this, okay? And this becomes 1 comma 0 point, okay? When their input is 1 for the log function, their output is always 0, okay? And the gn is bounded to 0 and 1, okay? Because gn is the output of the sigmoid function, okay? They are always bounded to this range, okay? And let's say the yn is 1, okay? When yn is 1, what should be our output? Means when one sample's class is 1, we have to classify that and samples as 1. And when that sample's ground truth is 0, we have to predict 0 as output. Okay? Are you guys understanding that? So when class is 1, we have to say that's 1. And for when their ground truth is 0, our output should be 0. Okay, that is simple thing. Okay, and we will this is log Cn graph, but we are having minus sign here, so our actual loss functions will be like this. Okay, so this is the graph we will use. Okay, loss is minus ln Zn, and our Zn will be bounded here, right? And we will minimize this loss L, right? We will minimize this loss L, right? During the training, we will always minimize this loss L, and we'll learn the parameters, corresponding parameters, W and B, okay? I mean, in this graph, and when Z is bounded, minimizing loss minus ln Zn means we will eventually make Zn goes to 1. Okay, so in this bounded range, if we minimize this minus ln Z, that is making Zn goes to plus 1. Okay, are you guys understanding this? Okay, that coincides with our objective. Okay, so when yn is 1, we want to make our final output Zn close to 1. Okay, I mean, in that case, if we threshold Zn, Zn will be larger than some threshold. Okay, 10 to larger than the threshold, and eventually becoming to predict those samples as one class. Okay, and okay, and the same thing happening in this 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 part. Okay, so let's say minus ln 1 minus gn. Okay, this is you can think this is the loss functions for this minus ln 1 minus gn function. Then now Gn is also bounded to 0 and 1 range, okay? And we are wanting to minimize this minus ln 1 minus Gn. That is meaning that we are wanting to make this part close to 1. So in that part, the y values will be minimized, okay? That is meaning that Gn will be eventually goes to 0, okay? Close to 0, okay? Are you guys understanding this? Okay. So when yn is 0, by minimizing this, we can make Zn goes close to 0. And when yn is 1, by minimizing these loss, we can make Zn go close to 1. Okay, are you guys understanding this? So that actually coincides with our objective. Okay? So because of that, and this binary cross entropy loss, we call that as BCE loss. We use that for binary classification. Okay. And when using this BCE loss, okay, I will finish soon. Sorry. This is some data definition, and I mean this is the same training code you see before, okay? And this is the same optimizer, the stochastic gradient descent, but the thing changed here is the loss function. MSE loss previously used, but now we see BC loss is used, okay? Because our data now is the classification data, okay, rather than the regression data. I will further explain about that next class, okay? So yeah, so this code, I will further explain that later, but the thing you have to understand here is the same flow of training code is remained, but only the loss function has been changed. Okay, okay. For today, we can finish here and see you next Monday. Okay, thank you.